And the reason that's a problem for physicists is that consciousness is subjective. Physics, from their viewpoint, is an objective science. The two don't really have anything to do with each other. And if you are a physicist working in objective science and you do experiments that have something to do with the subjective, that's not good for your career. You see, so it's not what they do. So they don't see that as being in their ballpark, something they worry about. Now, these are just straight quantum physics experiments. There's nothing, there's no consciousness meter that you have to plug into it. There's no physical kind of consciousness connection. So it's just a straightforward quantum mechanics experiment. But the consciousness connection, I mean, they've all heard of the consciousness connection, but it's very controversial. And people tend to shy away from stuff that's controversial. So we had trouble with that. But recall that one of the premier sites for doing research in the subjective world, in the intuitive world, was Pear Labs, Princeton Engineering Anomalies Research. Pear Labs is not functioning now, but it went for about 20, 25 years, did lots and lots of exceedingly good work where people were using their intentions to modify all sorts of things. But in the beginning, it was probability distributions. They'd set a little robot on a circular table, set it in the middle of the table, and they'd turn this robot on, and the robot was programmed to move in random directions. So it would have as equal opportunity and probability to move right as left and forward as far as back. So it would just sit there and dither around in the center of the table as it was making all these movements, but randomly, so it never left the center of the table until someone came in with their intention to bias those random movements, and that little robot would fall right off the edge of the table, you see, which was, of course, impossible. And that was done with a person's intent. So they did a lot of experiments like that. And their protocols were excellent. And the people running the experiments, tended to be physicists. But it wasn't Princeton physics department. It was the engineering anomalies research. So why did this physics study end up in the engineering department? Well, there's a good reason for that. Physicists have a lot of investment in their theory, and their theory is very solidly materialistic. Okay. Engineers have very little investment in theory. Engineers just want to know, does it work? That's it. Is there something meaningful behind the research? Great. Does it work or it doesn't work? That's an engineer's viewpoint. Theory, who cares? If it works, that tells us something. If it doesn't, that tells us something. And there's no real connection there to, oh, but this is against our rules, It shouldn't work, and we really don't want it to work because that would confuse us all. So engineers don't have that problem. That's why Pear Labs was in the engineering department. And that's why Farbod represents the engineering department, because we went through probably, I don't know, a couple of dozen physics departments with 0 results and 0 takers. And first time I talked with Farbod, he said, great, sounds good. I'm doing quantum work already in quantum encryption. I'd be glad to do it. Sounds like fun. Hey, do you know anything about consciousness? Because I'm real interested in conscious computers. And I said, oh, we're going to get along together real well. Yes. So the C word didn't frighten Farbod at all. He embraced the C word, and now he's been working on it. It took us a long time to get the contracts in place. And those things sometimes just take time, because if it was just Farbod and I that had to do a contract, we could have done it in an hour. But it has to run through countless administrators as well, and I have to run mine through lawyer, and it just takes time to do all that. And then you send it back, and then you send it back again because this wasn't right, and you do it back. And after 6 or 7 of those iterations, you're 6 months into the process of getting the contract done. So that takes a lot of time. And then I've been traveling so much that I was slow on my end sometimes at turning things around because I haven't been home to do that. But anyway, we got that contract in place. It's a year-long contract. And it's just a couple of months since really it's been in force, since it's all the legal work's done. And of course, the person doing the work is told by his management, don't do any of the work until the contract's in place, right? That's what the legal team and that's what the administrators tell you. So Farbod was actually doing the work, but just quietly where nobody could see him, even though the contract wasn't really in place yet, because he was interested and he wanted to do it. So, he was kind of working on it on the side over the summer, but you can't get so much done that way. So really the contract started in about the same time school started, which is not really a good time, Professors are busy when school starts. They got a whole lot of things happening all at once. So for the last, since school started sometime probably in August or early September or middle August or something, right? Something like.
It was actually approved last week.
Yeah.
It was approved last week.
Last week?
The formal approval.
Formal approval for him from his management was last week. So he's been working on this for several months, and now he can admit it. Yeah. So we haven't been working on it very long, and it's a very challenging problem to set this up and get it to work right. To get one photon at a time. Just imagine how difficult that is, to get your equipment to look at one photon at a time. It's a tiny little thing. Actually, it isn't a thing. It's just a probability. And it changes its location very, very fast. So it's a challenging setup. So here we are, 1 week into the contract, and Farbod's going to give you a little report on some of the challenges he has and about when he thinks or how long he thinks it might take to get results and what we can look forward to. And I know all of you have been looking forward to this. I must get 10 emails every day that says, Tom, what's going on with those experiments? We haven't heard anything for a couple of months. And I'm thinking, the last time I gave you a report, I said I'd let you know when I had some results. But another week goes by and haven't heard from you this week. Well, how are those experiments doing? It's going to take a little longer than that. We're going to be months away from the possibility of a result. We're just getting the equipment. Farbod has just looked up a piece of equipment that we're not sure we have to buy, but it's a possibility. And it only costs $10,000. And to buy things that cost that much in a university takes a lot of time, because Farbod has been very kind to us, and he is trying to convince his university to buy that equipment because it's equipment that they can use, the thing. So he's making a case for getting that done. So he's really given us a wonderful price, and is trying real hard to give us some good results for a low ticket, which will leave us more money to build a good story and video of this whole project, so we can make a real good documentary of the process, which will then spread the whole idea much farther and much wider. You see, so it's great to do the work, but getting the work out to where lots of people know about it is another daunting process, and that also takes a lot of time and costs a lot of money. So Farbod, tell us where you are and where you're going.
Hello everybody, my name is Farbod Khushnud. I'm a faculty at Cal Poly Pomona in the engineering college, and it's my great pleasure and honor to work for Tom on this project really and learning from him. So I'd like to give you a little bit background about what I do and the relation to quantum, and then explain the actual test. So also I'd like to thank Professor Human Ohadi, who is sitting there, so who introduced initially to me to Tom, so gave me this opportunity to be able to work on this interesting project. And so I've been working with Professor Ohadi maybe for more than 10 years on different projects, research projects. Basically, the actual project was for only 2 years, 2009 to 2011, which we worked on a kind of a nano-electromechanical engine, which we published the work. But since then, we have been friends, so mostly. And then he published that interesting paper with Tom maybe a few years ago.
Stand up, Human.
And
See who you are.
So I've had the opportunity to work with both of them before. And my background related to quantum, because I'm an engineer. So basically what we have been doing before I met Tom was how we can apply quantum to engineering systems, basically. As you know, there's a lot of work on quantum computers, quantum computing. People are trying to do a lot of work on that. But nobody really has applied quantum capabilities to engineering systems, let's say robots. So we want to know how we can integrate quantum capabilities, let's say quantum entanglement, quantum cryptography, to robotic systems. So that's what I've been doing in terms of my background. So yes, we're trying to basically say, as you may have heard about in quantum, they call Alice and Bob, so they're entangled. We say, how can we apply that the same quantum technology, which is Alice and Bob, to robotic systems? So we can call them Alice drone, maybe, Alice robot, maybe, or Bob robot. So basically, these are the things that we want to apply in the engineering domain. And so, for example, in this case, we have a Bob robot and we have Alice robot, so they're communicating, and the communication is by laser, which is creating photons and then receiving the photons on the other side on the other robot. And then basically there's kind of a quantum cryptography communication, which we can use it to control the robots. So it's another just figures. In terms of entanglement, we are just using the same technology that physicists have been developed on quantum entanglement. And we say, okay, now if we have that quantum entanglement and put them on the sensors, basically, just put the sensors on or what is actually in terms of sensor is a single photon counters. If you put the single photon counters, which you see in this figure on the top, on two robots, and we send two entangled pairs of photons, can we entangle these robots so they can do the same things without communicating with each other? Okay, so they're entangled robots. So these are just my background. So again, it's another figure. And we have published this recent. There's a recent publication. There's available to public. There's another one. Some of the work actually I did with JPL. So we have some co-authors on this paper. So some of them are accepted, some of them in progress. So these are all the technologies that we are developing and the system that we have on the testing. We also work on the theory background, how we can really combine quantum mechanics to classical dynamics in terms of dynamical systems, not in terms of quantum computers or in terms of molecular systems, with actual mechanical systems like robots. So what does it mean? What the control system look like? Not only that, we also try to teach that now, bring it to teaching. So we want to teach a course that is combination of control system, mechanical system, and quantum. So I would like to teach that now. I'm developing a course to teach that. And so in terms of research of the application, so for example, the police department is interested in our quantum cryptography, quantum entanglement for robotics application in terms of security and emergency response. And as I mentioned, I've been working with different people from different universities. JPL, I have the publication I've been with, the latest publication was with JPL. and Brunel University London, and University of British Columbia in California. So this is just a little vision about that I think that the future. So we have to be prepared for this future. So basically we will have a lot of autonomous systems and robotic systems in future. So how do we really deal with this network of huge autonomous systems? And I think quantum is a good solution, in my opinion. So now, with that background, this is the experimental setup that we have been trying to work and we have been trying to do in the lab since just the start of the summer. And I've been working with one of the students, Nathan is here, Nathan Swetlov, and Anand Handam is my colleague from Cal Poly Pomona. So they have been helping me to set up this experiment. So when you have the double slit, they are about a micrometer apart from each other. So the slits that we are talking about that we want to do the experiment. So now one of the questions is, as Tom may show you the experimental setup, maybe the configuration later. I'm not sure if you have planned to show it.
I can if you ask the question.
So
if anybody wants to know that, I can draw a little diagram if you're interested in that. But
yes. So
physics usually bores most people.
So now the question is how really we set up, if there you have two slits that are micrometer apart from each other, how do you place other equipment just right after that? So we have to come up with some solutions. So Tom has been helping us with solutions really. So how we actually can do that. So give us direction, give us guidance how to do this kind of experiment. And we have been trying to do that in the lab. So because we have the equipment, and Thomas has been supporting us, we have been learning also. There's a learning curve for us also. It's not something that we all already know about it. So everything is in progress, and we're hoping that we can get some results sometime. We don't know yet when we can get results, but we are working on it. We're working on it, and the work is in progress. And we continuously work. We never stop. Yes. Okay, thank you.
Thank you. All right, so now you've heard what's going on, from the guy who's doing the work. So I'm not trying to trick you. Okay, like I say, we can talk about anything, and I guess we should start putting hands up to see what the questions are.